Okay. Let's see where it was. I guess we can move it out of here. Our 450. Let's just create a folder. All right, everybody online can see the screen, hear me, all that jazz.
Yep.
All right, so let's pick up where we left off last time and get MergeSort working. Let's see. If I remember correctly, right at the end last time we had the it was dividing everything up, but we were having a weird thing with like the number of children. I think it's because I looked at it. I think there was because we had an extra pause in there. Row. It's a very weird result to a running a program. Let's give that a secondary college try here. I wonder if it doesn't like my shared memory key being hard-coded. So let me just fix that real quick. I think that'll probably be the issue. We have shared memory in here. Just do this. I just want to get the thing to generate the key as opposed to my hard-coded key. This guy. What? Do we do just hello world first? Make sure hello world works in our, pretty funny actually. There's hello world, GCC, hello. Yeah, actually the whole thing seems to be running funny. Restart the virtual machine real quick. If this doesn't work, we'll just do it in the website thing to finish it.
Probably Clancy's fault.
Well, I hadn't used the virtual machine here, but maybe, I don't know. I mean, it's possible it's something that worked on the website thing, but and the thing that made sense to me was the virtual memory, instead of hard coding the key, using the token generator for it. But I certainly was not expecting a crash like that. This is what's happening. I will figure out what's going on. Because I mean, this was running last time, right? Yeah, and our problem, so it's running completely now. The problem was we had an extra pause in here rather than just letting the parent wait for both children to return. So we had two pauses and it was never getting past the second one. That is really frustrating. Why is that failing like that? Well, let's get it working over here and then we'll try copying it over there. We can always debug it later. I'll debug it offline. It all looks okay. All right, so in any case, we've shown that we've divided up our, I think we're displaying a couple of extra times here, but we've shown that we've divided up our stuff where it's got the left and the right child with those processes working through the things. And let's see, am I able to make this more full screen or something? Or we'll just roll with it. We'll just roll with it. All right, so in here in the handler, right now we are, I have a little message that says once both of our kids have returned, that means the left and the right half of our list are sorted, right? So we know that the begin to end is sorted. Now, what we can do here is, if you remember, we have begin one and we have end one that was created in here at the child level. We might need to, well, we could do it as a global, but we could also just figure out where the begin and end should actually be again. I'm just going to steal those two to make life a little easier for us inside of this handler. So inside the handler here, if it's time to merge, that means we know that the left half of our shared memory is sorted from begin to end, just that section of it. The left half of that section is sorted. The right half of that section is sorted. And now we need to perform that merge step where we pass it where we say, here's the portion of the array we're interested in. We need to pick a winner and then copy the answers back over to the right places. All right, so remember with merge step, where's Keynote? There it is. So we'll do like a sample for the merge step. So the merge step might look like, we might have a list that looks like that. 1, 3, 2, 8. And the reality is begin here is whatever bucket that is. We can assume this is 0 in this case, but this could be bucket 6 through bucket 7, 8, 9. So actually, let's assume it's that, so that way we don't. So the portion of the array we're looking at here is 6, 7, 8, 9. So those are the buckets of the array that we're looking at. And we know that the first half, 1 and 3, are in order. And we know that the second half, 2 and 8, are in order. They would only be in order if the children have already reported back that I have finished my job. Okay, because a child's job is to ultimately sort their portion of the linked list. With our understanding that the thing that ends our what used to be recursion, but now ends the duplication, where we're no longer creating 2 children, happens whenever we get a 1 list. That's when the list is trivially sorted. So when a list is not trivially sorted, but we still now need to sort it, we perform this merge step. So what we're doing right here is the merge step in MergeSort. All right, so I'm looking at a begin of 6 and an end of 9, and these happen to be the values. And as a human being, we can see that the first half is sorted, the second half is sorted. So we want to go ahead and calculate begin 1, end 1, even though we had previously calculated them because we were using some variables. Probably are safer here to just go ahead and locally rebuild those values. So we want, well, I don't need to put it in front of it. So we'll say begin 1 is equal to 6 in this case. End 1 is equal to, actually, we'll write it generically. So let's say begin is 6, end is 9. Those are those 2 values. So begin 1, the first bucket of the first half, will be at bucket begin. I'm going to leave end 1 empty for a second here. Begin 2, we'll say, is end 1 plus 1, whatever is 1 past the midpoint. And then end 2 is equal to whatever end is. So we know that end 1 that we calculated below was end plus begin divided by 2. That gets us our halfway point. So in this particular case, 6 plus 9 is 15, divided by 2 is 7. So that's the end of the first half, is bucket 7. Okay, so this will be begin plus end divided by 2. That's what end 1 will be. So now we'll know the beginning and ending of the first and second half. Okay, so what we do for the merge step is we create a second array. Let's copy these. And this guy, that's of the same size. So this will be 0, 1, 2, 3. And this guy will initially have nothing in it. It is interesting that it took more underscores than characters, but I think it took 6 underscores to fill the same gap as four numbers. So now what we need to do is we're keeping track of the beginning of the first half of the list and the beginning of the second half of the list, and we want to start picking winners. We're merging these 2 halves together to give us a single sorted collection. All right, so we're going to ask, now we know that we are still on the beginning of this list, that we're still in a legal position of this list if begin 1 is less than end 1. And if we could actually even create another variable, if we want to just say pause 1 is equal to begin 1 initially, and pause 2 is equal to begin 2. That way we don't change begin and end. So now we can say we know that we have not finished placing all the stuff from the first part of our array here, as long as pause 1 is less than end 1. We also know that we haven't finished placing everything on the right half if pause 2 is less than end 2. So right off the bat, we'll say is pause 1, So I'll give ourselves our actual values over here. So we're going to say begin 1 is equal to 6, end 1 is equal to 7, pause 1 is equal to 6, begin 2 equal to 8, end 2 is equal to 9, pause 2 is equal to 8. So both pause 1 and pause 2 currently point to legal places because they're both, so pause 1 is less than end 1, less than or equal to end 1, because end 1 is actually an actual place. It's not 1 off the end, it's the actual last element. So since pause 1 is less than or equal to end 1, and pause 2 is less than or equal to end 2, that means that pause 1 and pause 2 both point to real places. So we're going to compare them. We're going to say, who is the smaller value, a 1 or a 2? We're going to say, that 1 is our, that 1 is our initial winner. And then we'll increment pause 1. So pause 1 is now a 7. Is pause 1 a legal place? Is 7 less than or equal to 7? It is. Is 8 less than or equal to 9? It is. So which is the smaller number, a 3 or a 2? That is the thing that pause 1 points to or the thing that pause 2 points to. 2 is our smaller value. Oh, that's why, because I had spaces. Makes way more sense now. Oh, yeah. All right, so 2 is our winner, and we increment pause 2. Is pause 1 and pause 2 both legal values? Well, pause 1 is less than or equal to n1. Pause 2 is less than or equal to n2. So which is the smaller value, a 3 or an 8? It's a 3. All right, and because that was from pause 1, we increment pause 1. Is pause 1 less than or equal to n1? It is not. So we cannot, we're done placing everything on the left half. So then we say, well, we only have one possible person to place now, and that's this guy pause 2. That's our 8. We'll go ahead and place that. So we have our 1, 2, 3. All right, now this is our temporary array here. So this holds the values in the correct order. And the temporary array is bucket 0, 1, 2, 3. There's 4 elements in it because there were 4 elements in the portion of the array we're currently interested in. So now what we need to do, and this is our shared memory up here. So now what we need to do is we need to copy our now sorted values back over the same places in shared memory. So we'll copy the 1 over the 1, the 2 over the 3, a 3 over the 2, an 8 over the 8. And by doing that, by putting that into shared memory, those changes are now done throughout all of the different children because we've done it in real memory that's shared among all the children. That portion of the array is now sorted. That makes some sense? All right, so we want to write the code that accomplishes this piece here. So this merge step. And what we can do is, we'll write it in a little function. So we'll say void merge, and this guy will take in a int array, which will be our shared memory we'll pass along. It will, and our shared memory is a global variable, right? It is not currently. We're going to have to make this guy global. Frankly, then it doesn't need to take it in here, but it's not going to hurt anything to take it in there. So there's our shared memory pointer. So then down here, We'll just set that value. In merge, I don't know, it is global, we don't really need it. So let's say int begin 1, int end 1, int begin 2, int end 2. All right, so now we have our function that's assuming the existence of this shared memory pointer. You know what? I prefer this. I just like it better. I'm going to have this guy take in an int pointer. And then what we'll do down in here, I'm going to go ahead and grab those lines that calculate begin 1 and end 1, all those things. So when it's time to merge, we go ahead and set begin 1, end 1, begin 2, end 2, and then we go ahead and call our merge function, passing our shared memory pointer. That's what it was called, right? CHMP. Begin 1, end 1, begin 2, end 2, like that. This is the guy whose job it is to do what we just did right here. So the first thing we're going to do is we're going to create a new array capable of holding the same number of elements as the number of elements in the from begin 1 to end 2, that number of elements. All right. So if end 2 is 9 and begin 1 is 6, we need end 2 minus begin 1 plus 1. That's the number of elements that we need in our temporary array. So up here in merge, we're going to create our temp array, int temp of size n2 minus begin 1 plus 1. That's the number of buckets we'll need in that array. All right. So what we just did there is we created this dude down here, this array. Okay, which doesn't necessarily line up with the begin 1 to end 2 numbers, but they should both be the same size. The section of our shared memory and this temporary array should be the same size. Okay. So now we'll go ahead and set pause 1 equal to begin 1, pause 2 equal to begin 2. Those are our pointers that we're going to use to walk through our list. All right. Now we know, in fact, I'm going to go ahead and just write I'm going to say int size is equal to this dude. So size is the number of buckets. We'll build temp to be that. We know that the number of elements that we need to place, really, if you think about it, we're like judging races, right? The number of races that are going to be run are size number of races. Some of them will only have one competitor potentially, right? But that's the total number in our little example here. It's the total number of races that are going to have to run. So we know that we're going to do something size number of times. We could certainly have put it in a while loop that says something like while pause 1 less than or equal to end 1 and pause 2 less than or equal to end 2, while both of those things are true statements, keep going. That will be size number of times. Those are synonyms for each other, right? We know how many elements we're going to be placing. All right, so we have 3 different things. If both pause 1 and pause 2 are legal, do one thing. If only pause 1 is legal, do another thing. If only pause 2 is legal, do another thing. Those are the 3 different things that can happen here. So these are one-man races for these 2. This is we actually have a competition. So if pause 1 is less than or equal to end 1 and pause 2 is less than or equal to end 2, If both of those things are true statements, we have an actual race to run. So we'll ask the question, if AR at bucket pos 1 is less than AR at bucket pos 2, if that's a true statement, we want to go ahead and place the winner inside of temp at bucket I. So temp at bucket I gets the value AR at bucket pos 1. Then pos 1 plus plus. Okay, so if AR at bucket pos 1 was smaller than bucket pos 2, record it inside of our temp array, increment pos 1. Else, if they were both legal and pos 1 wasn't the winner, pos 2 must have been the winner, right? So we'll say temp at bucket I is equal to AR at bucket pos 2 plus plus. That's if they were both legal positions, and we're going to compare them. Else if pos 1 is less than or equal to N1, that means pos 1 was a legal position. So we'll say temp at bucket I equals AR at pos 1 plus plus. Else, pos 2 must have been the winner. Temp at bucket I is equal to AR at bucket pos 2 plus plus. All right, we're going to do that size number of times. Once this loop is done, temp should be filled up with the merged version of begin 1 to end 2 in our list. So now we need to copy temp back over AR from bucket begin 1 to end 2. We're making sure we're overwriting the right portion of that array. Make sense? All right, so we could do this with a couple of separate variables. We could say int temp pos starts off at 0. And you could do this inside of a single for loop because for loops do allow you to define more than one value, but we'll just use this as standard for loop. So we'll say for int I is equal to begin 1, I is less than or equal to N2, I plus plus. So we're going to walk through AR from bucket begin 1 all the way up to and including N2 and place temp at bucket temp pos each time. So AR at bucket I gets the value temp at bucket temp pos and temp pos plus plus. Okay, so this copies it back over. This guy here fills temp up with our correct answers. And temp is this local variable that's going to die when this function ends. But AR is our shared memory. This copies the contents of temp back into AR, overwriting what used to be there, but now it's should be complete. Ooh. Okay. So down here in our signal handler, once we know we need to merge, when both children have responded back saying, hey, we're done with our portions, we'll go ahead and call merge with the shared memory, even though it's global, we didn't need to pass that to merge, but I did. I passed this in. It's going to come into merge as AR. Along with the beginning and ending of the two halves. It's going to go do its thing. And then this child's job is done. So since this child's job is done, what does it do? It lets its parent know that he's completed his job. That is, he has sorted the portion of the array he was supposed to sort. Make sense? Okay. So now let's see where we're going to do our displays. I'm going to take out our displays along the way, and we just want to do a final display. Funny thing is, how do we even know who's their final? We're going to kind of need to keep track of the final parent, like the original parent ID, like who me? The last one standing. So we can go ahead and do this. We'll have an int orig PID. And when the program first starts, right off the get-go, we'll go ahead and say orig PID is equal to get PID. This is the original parent's process ID. And then what we can do in here, right before we exit, we can just ask the question, if get PID is equal to orig PID. And we got so many kids running around at this point. If I'm the original, then I'll go ahead and do a display from begin to end, which I think I have as globals, right? No, I don't. It currently has an error in it then, so we need to have, where did begin and end come from? Right here. So we need begin and end to be global variables. So we have access to them throughout. That actually might have been the problem over there, is it's possible this website allows for shared variable scope just to make the way it makes it work, because I didn't have begin and end set up as global variables there. I was using, I just started using them in here. So that wasn't a problem. But I do need begin and end to be values that can be shared among all the children, even though we weren't changing them based on which child it was. We just made those variables accessible from up here. Okay. So where's my handle here? If I'm the original process ID, if I'm the original parent, we never changed that value. We said it once, and after that part, we had all of the spawning multiple kids, things like that. Never changed that value. So we have the process ID of the original parent. So if my process ID is the original process ID, go ahead and display the entire array, which actually we don't even need to say begin end there. It should be the correct begin end though, because we really could say 0 to num elements or whatever I called it. Yeah, num elements -1, but begin and end for the original parent should be those values. We didn't change them, so that'll be a good test as well. Somebody didn't, are we in an infinite loop? We are calling merge in here. Let's just do a print before merge. And then we'll do another print after merge. Just making sure we're getting to both sides of the coin there. Oh, maybe I just didn't scroll down. There it is in order. And what was my original? So I mean, it looks like it worked. Yeah. 1, 2, 3, 6, 7. I think maybe what we're seeing here is when it's getting CPU time for the IO, a couple of the parents are actually finally able to display that they finished. Not that they didn't already do their math, but their display got out to the screen later on, because there is our sorted list. So that's fully multi-process sorted MergeSort. And this would be an example of where MergeSort shines. Because MergeSort itself, anytime you're dealing with recursion, it probably doesn't equal performance. And when you're talking about sorting algorithms, we might say from an academic perspective that the more complex the sorting algorithm seems, the faster it's supposed to be. Because why else are we torturing ourselves? Something along those lines, right? Fair enough. Hopefully we're reminded, because you've seen MergeSort 2 or 3 times now through your career, but each time you see it, it should feel a little easier. But hopefully at this point, when you're looking at that merge step, this guy here, this looks somewhat complex, but it's just a bunch of if statements, right? There's not a whole lot going on there rather than just saying, if this is true, do this. If this is true, do this. If this is true, do this. Just we got curly braces all over the place, and it just kind of at a glance looks like it's more complex than it might otherwise be. But in general, you might have the opinion that the more complex a search or a sorting algorithm seems to be, the faster it should be. Otherwise, why are we putting in this extra effort? And this is where we start blurring the line between what's the right tool for the job, and it kind of depends on what is our compute source that we're using for this particular, that's going to be running this particular algorithm. If it's a heavily multi-processed computer, or multiprocessor computer, where you maybe have an 8 or a 16 or a 32 or a 48 core processor, and they exist, right? NVIDIA has a server class processor that you could actually buy that has 48 cores in it. It's expensive, but it does have 48 cores in it. So technically you can do 48 things simultaneously. Now, more commonly, I mean, probably several of us in here have a machine that has 4 cores in it, quad cores. Those are pretty common. In fact, I think almost every computer today, that you buy, is going to have at least 4 cores. So a Core i5 CPU has 4 cores in it. I actually think maybe the most up-to-date Core i3, which is Intel's budget pleaser, still has 4 cores. For a while, it was a 2-core processor, but I think the most up-to-date one, like, they might not know how to not make 4 cores anymore. Now the differentiating factor is what's the maximum turbo speed, right? It's like, well, this is quad core. It's 2.14 gigahertz up to 12 gigahertz. They don't go to the high, but up to 5 gigahertz. That means, this is going to happen in short bursts, because if we were running this at 5 gigahertz at all time, your machine catches fire. So you don't sell it as a 5 gigahertz processor for that reason. But in any case, even in a small example like that, where you have 4 processors that can technically do things at, 4 things at once, and then, you start looking at like their hyper-threading crap, where they say, we actually have, 4 cores actually means 8 logical cores, which is a fancy way of saying we could almost do 8 things at once. What they're really doing is something called pipelining. which talk about in the 325 class, pipelining, which just is a way of setting things up so that the CPU can kind of get a jump start on the next instructions during context switching, that type of setup. But even if we just look at it from a four core reality, you're still dealing with a situation where we can have 4 separate workers in actuality working on a data set, potentially being able to sort it 4 times faster, potentially, right? Now you also have a world of distributed computing. So if we just go back and let's start getting some of this into the slides. So we might say, why implement MergeSort with multiple processes? So we might say, we could implement using multiple threads in a general case. What's the difference between a thread and a process at the operating systems level?
They're part of the same process, but they can different parts of it.
Okay. I think that's more of an organizational aspect of threads, whereas when you create threads, you give it the function to run, as opposed to here where we're creating a duplicate, where you just kind of pick up where you left off, where you got this clones there and you're trying to figure out who's who, right? You literally are a brand new, true to life process. So what you just said is true in terms of how you use it, but at the operating systems level, how does the operating system view a thread differently than view a process? But yeah, so the operating system, one of its jobs is the CPU scheduler. So when you have 3 processes, true processes, the CPU is going to give, let's just pretend we're in a world of pure fairness, it's going to give each of those processes 1/3 of the CPU time, some amount of CPU time, right? Whereas if you have one process that has 3 threads, each of those threads is getting a portion of their parent's process CPU time. All right, which is actually, we can say, a better solution for not letting your operating system fall prey to attacks through just an infinite loop that just keeps creating multiple processes. We talked about how the fork command can lead to that, where you actually run out of process IDs on the operating system, where you can't even launch a terminal to kill off process IDs. And we actually saw it several classes ago when we had the same memory locations, but it actually wasn't the same memory because it was housed inside of a virtual little container for that running process. We've kind of come a long way with even C programs running in a modern day like Linux operating system. So a full process gets its own time on the CPU, where a thread gets a portion of its parent's time on the CPU. A full process gets its own time on the CPU. A thread gets a portion of its parent's time on the CPU, which is safer, right? But potentially leads to less performance. So when would we actually want processes instead of threads? Because that's what we've done here, right? We've made processes, not threads. And everything we've said in the last 5 minutes kind of indicates that maybe this wasn't the smartest idea. Threads seem better than processes. And that's something that we get lulled into, I think, as computer scientists, is we view threads as being the upgrade to like the fork system call. Like, oh, we don't need to create a duplicate process anymore because we have threads and threads are better. When might having an actual process make more sense? And that's something that's just starting to become kind of common, more commonplace. Go ahead. Okay, but threads would be able to pull that off. Because in a threaded situation, it would be like, okay, I'm standing by the oven. I'm ready to make this lasagna. I'm going to send my runners out to go get the cheese and the noodles and stuff like that. And I'm going to sit here and I'm just going to wait for the threads to come back. Not really any different than waiting on your kids to report back, right? It really has to do with maybe the potential performance of the situation. If I'm sitting there and there's only so many minutes in the day, threads would be sharing my minutes, whereas those processes would be taking advantage of whatever compute resource there is. And that's the kicker here, is what is our compute resource? That's the thing that keeps changing in modern day computing. If we roll back 20 years, our compute resource was a single core processor. It could do one thing at once, right? Threads, processes, doesn't really matter. It's only doing one thing at once. Okay. If anything, threads require a little bit more overhead at the process level, whereas the multiple processes is like, look, yeah, you might be clones, but you're just some other process running on here, just like any other process, and the operating system already knows how to deal with generic process. So, but the idea of what our compute resource, what our CPU resource is, has changed over the years to now, multiple core processes, to now cluster computing, right? Where you can have a farm, a server farm that has 200 computers in it. Each of the computers has a multi-core processor in it, and your process gets sent to whichever of those computers is currently most available to work on it. All right. What you then need is you actually need a physically separate entity, not some portion of a running process on one of those machines. You need to have a whole process that you can say, okay, I'm not going to run you locally. Instead, I'm going to pass you off to this other computer, and he's going to run you. It's a process, a fully built process, and he's going to run you locally. All right. Now, that then implies there must be some sort of framework that sits above, like an umbrella that sits above those that farm of computers, because we still have this idea of inter-process communication, right? But now those processes might not necessarily be living in the same neighborhood. Now we're making cell phone calls to Moscow, okay? 9 computers over. That makes sense? So we're still going to need that framework. Inter-process communication is still something that has to happen, but our definition of the distances across when that inter-process communication needs to occur keeps changing. And now with cloud computing, where those computers don't have to even be in the same warehouse. Okay, now you can have computers that are all over the world or even up in space, things like that, and they all need to communicate. You could potentially catch a signal from a process running on a satellite on a computer that's running another duplicate process in Arizona or something like that. And that has to be managed by some framework that links all those computers together in some way and almost creates a distributed operating system. We'll always say, not yet, but soon. Okay, and I'll talk a little bit more about that on Friday, but between now and Friday, maybe flip back through the slides and look at some of the things that we've done since midterm. Since midterm, we've done a lot more programming, right? So the exam is going to be probably 70% programming, 30% some stuff that's more framework things. So we'll go over anything you want to go over on Friday in preparation for the exam. I'll go through the slides telling you kind of what I think might show up on there and that kind of jazz, but we'll kind of finish this conversation because this is kind of where the current world of operating systems is sitting. What comes next? This idea of a distributed OS, which bottlenecks, but we'll talk about the bottlenecks next time. Questions, comments, concerns, bribes? All right, I'll see everybody on Friday.